guys, it's 11:15. We're going to get going. Hi. Oh, no problem. You guys want to come on up? Hi, everyone. My name's Gary Lamb. I wanted to introduce myself today and kind of go through a little bit about my background so you guys know who's in the front of the room talking to you. I've been in the virtualization space since about 2000. Started out with the first copy of VMware and had a profound impact on my life from a technology perspective. So I was an old mainframe guy, moved up from the mainframe, and I said, wow, this is just like what I learned in college. So I was built for virtualization, I think. Virtualization is the Swiss utility knife of what we do. So when we look at my background, I ran a security practice for internet security systems back in the day. Worked with Chris Klaus personally on threat detection, wound up building the Wells Fargo network for about 6 years, working with a vendor that supplied all the hardware there. So I looked at things from a very large scale. Once you have Wells Fargo on your resume, you don't get rid of it. So I handled Wells Fargo when I was at Internet Security Systems, and I got Oracle business to business from a security perspective. And that was a great ride until IBM purchased Internet Security Systems, and we all got fired. So a little impact on my life. But I happened to be at NVIDIA that day when we all got fired. And NVIDIA said, hey, it's not the name behind the company, it's the people behind the company, stay. And we wound up building one of the first virtualized environments in the chip sector in Silicon Valley that was 100% VMware. During that time, we got crazy because in NVIDIA you could get crazy, and people paid you to get crazy and think about things that were outside the box. So what we started doing was we started thinking about abstraction of any time that we could take something that was a piece of hardware and abstract it, we could work with it faster, cheaper, and better, and it could move. So IP addresses could move between data centers. DR was simple because it wasn't a physical disk. It was a file structure that now was encapsulated and it could be moved. So this concept of encapsulation is one of the key components that we start using, and we keep reusing it. And what we found was there are 4 pillars of our world in IT. There's networking, there is storage, there is compute, there is memory, okay? Those 4 pillars can all be abstracted at some layer. And when we talk about virtualization, we're talking about a technology that we're skating the system. We're cheating the system, right? So the first mainframe cheated the system by time sharing, right? So when we take that and we time share or cheat the system around hardware, we have to figure out ways that we can accelerate things and make up time. So time is one of the most important things that we talk about when we build infrastructure. I'm giving you this framework because I'm throwing out all my secrets. And we're going to throw out some things that I didn't do right in the world. And those are the things that I'm the proudest about, because I learned a lot more than things when everything goes right. So when we look at this, we look at disaster recovery. We usually have to spend a lot of money to do disaster recovery and business continuity because we need like for like, right? All the way down to a switch, down to hardware, down to a disk drive, down to systems. And how do we preserve that image of that system? So today we'll cover some of the points that we have to look at from an architecture perspective, and then we're going to cover some technology that we think is very innovative that allows us to have a Swiss utility knife at the network layer to recreate almost everything at a virtualized level that we have in the physical world today. That's routers, switches, OSPF instances, BGP instances, all can be created at a functional level inside the hypervisor and leveraged quickly so that we can stand that up quickly and use it in a DR perspective. So that's kind of the background that I wanted to cover. And then today is very open. Please, when we talk about something, we're here to answer questions and talk about what we're doing. So any questions so far? Sorry for the folks, but my name's Gary Lamb. So one of the first things that we needed to talk about was how many folks have a DR project that's on the table that you got to do, right? Everybody should say yeah. That's why we're here, right? So the important part about the DR project is we have to have management's buy-in, because there's a ton of money that we're going to spend, and how we spend the money is the most important thing that we look at to whether we're successful at the end of the project or it's a train wreck. And we don't want train wrecks. So how many folks have physical infrastructure that they still need to deal with? Almost everybody, right? So when we look at the virtualization strategy that you have, what would you say the percentage of virtualization is that's deployed in your production environment that you're picking up? Just throw out some numbers. 80%? Wow. That's great.
Yeah, I say like 10.
10, seriously. What's driving only the 10? A SCADA or something like that?
Yeah, just the data size and actually the redundancy factor associated with it, and we'll basically CalCloud.
Okay.
New resources.
Okay, awesome. Anybody else want to share? 20? Okay, so that's the first major decision point that we have to talk about, because now you have physical storage objects, and if I were to be presumptuous and take a guess, 20% of your 80% is attached to a SAN, or is it a higher number than that? 75% of your storage is SAN-based storage that's driving the 80% of the open systems that are not attached. Because what this leads to is the question of how do I get at replication? How do I replicate that data? If it's a lot of DAS, direct attached storage, I'm going to have challenges. So I need to come up with a strategy to handle that. If it's SAN-based, right, that leads us to array-based replication, file-based replication, snapshots, all these different types of technology. And then we'll cover some viewpoints that I have and some different ways of attacking that. So that's an important question. Now the next important question that you have to look at is what's the RTO and RPO objectives of this? And these are hard questions to ask. So the recovery time objective is the time that it takes to restore whatever service, the assets of that service that are now missing. So let's say it's a business line system that has an Oracle database behind it. That could take us 20 hours to restore that. Depending how we stored it, it could take weeks to deploy if it's attached to physical hardware where the drivers can't be replaced. We have no way of inserting drivers to get to different hardware platforms that are now being refreshed by our vendor for us to restore to. So all of these are very critical components that you have to do almost in a workshop with your team. And you got to bring in all of your, I call them towers of power. In an organization, there's usually a storage team, there's usually an open systems team, a Windows team, a networking team, and a lot of times those towers of power don't operate real well together, at least in my world. And in the private sector, a lot of times they don't operate at all. So how do we bridge these gaps with the people and the process aspect of the technology? So getting firm grasp on the RTO and RPO objectives are very important. And how do we accomplish that from a technology perspective? So we've made a lot of mistakes in how we calculate that. So we used to, in the beginning, we used to say, hey, what's your backup? What are you backing up? How much data are you backing up on a nightly basis, okay? Well, that didn't work because the way Windows and the way Linux file systems operate, depending on the hash size and the value of the block, we're getting either more data or less data. But almost without a shadow of a doubt, you're going to get way more data than you ever expected once you start trying to replicate it. So the biggest part of this is think bigger than you could ever think about the amount of data that you're going to replicate, the time frames that you're going to replicate it, and shrink. Remember the need for speed and the need to be able to have tremendous amount of bandwidth, which those are always at odds with one another. We don't get bandwidth for free. We don't get speed for free, right? We have to pay for that. So we're going to go through some components on how we try and cheat the system to be able to do that. How many folks are struggling with the RTO and RPO objectives?
Mostly from the business, though. You know, from a technology perspective, you get a pretty good grasp on it. But when you go talk to the business, of course, everybody is a priority, a high, a number one.
Yeah.
It's kind of hard to get them to buy into actually truly what their RTO or RPO is.
So if we can't get that, we're destined to fail. And that's the most critical point, that if we don't get those objectives set realistically and we can't nail them down so that they're in a document that we're accountable for that document, then it's always going to come back to the architect or the guys in the technology position. You guys screwed up, we screwed up, didn't work, and now what do, right? So it'll come downhill. It never sticks up in the top room, right? It always comes downhill at us. So if you get that piece squared away, you're heading in the right direction. The next thing is where are we at in our hardware and software life cycles? This has a tremendous impact on the technology that we choose and how we get there. So if our SAN vendor, if we're a year into our SAN vendor's SAN, and we have 70% attach rate, 75% attach rate to the SAN, there's almost 100% chance we're not getting a new SAN, right? Or we're not getting any replication technology that we can start to leverage because there's no money in the coffer for that, right? So we have to live within the constraints of what we're given from that hardware and software recycle component. And then there's ways to abstract that to catch the data at different points, where catching the data in a different point in the stack is the most important part. So we'll cover that later in the slide deck. And then the biggest part is, how do we decide on replication strategies, snapshots? What's the technology framework that we're going to use? What's the impact of the technology that we're using? You can bring down the SAN with snapshots. You can bring down the network. There's a lot of things that have happened once you start replicating massive amounts of data and slowing things down. And then do we have an agent-based strategy? Is there an agent that we put in the guest machine or the physical machine to capture that data? So one of the rules of thumb that I look at is I never want to touch the machine. I never want to have any ownership of that client machine, because at the end of the day, the last person who touches the machine owns the machine for life. I run a service provider business too, so I manage 200 servers and about 150 desktops. So I not only talk about this, I live it, and I know what works and what doesn't work, and never touch the machine. It should be the cardinal rule, because you wind up owning it. And if you own it, you gotta fix it. And you'll be fixing it to the end of your career. So I didn't want to bore people with the slide deck, want it to be very interactive. But the next thing that we want to talk about in the slide deck is, how do we get the network right? And the network being right is the critical component to the whole project being successful. And we don't have to just worry about building a network at the data center. We have to worry about transforming an existing network and making it work in another location that's not our location, right? So you're going to back up to a DR facility. You're going to replicate your network. Depending on your business style, whether you're client-facing from a public sector or public sector perspective, whether your clients are the consumers of the data, you're going to have a strong internet presence, or you're going to have a strong presence that's your folks reside in your building footprint or in the footprint of your existing network. Well, what's the assumption that we made for testing the DR plan? Is the network gone? So tying it back one step in the management buy-in is, what are the scenarios that we test against? How do we judge success and failure? of this. So that winds up being a living document that you're building. You're building this document that we're testing against it quarterly, we're refining it, it gets better over time, hopefully, if you're serious about your disaster recovery plan. And we're adding more and more and more to it, which at the end of the day, we would be able to transplant your environment, turn up the user community, and we should be able to do that in 20 to 30 minutes, depending on the size of the network. So we have clients today that we can start 80 virtual machines, 80 to 90 virtual machines, 8 terabytes of data under management. That's a 20-minute process when the runbook works right, when all of the back-end infrastructure is designed correctly. That could take 2 years to get that to the point where 20 minutes starts that number of virtual components. So, pardon me here, I'm a Mac guy, so wanted to introduce ENS. And then we've covered all of this in my talking points, sorry about that. But let's get to the meat of kind of the subject matter. So one of the things that we found, we can solve all the woes that we've made in mistakes by bandwidth. So you'll see orange on there. Orange on there is fiber. So we worked really hard to put fiber in the ground to do this. And what happened was we started in 2002. We were working for a municipality where we had the we had the police station and city hall up in Nevada, and the river can run the opposite direction and wipe out the police department and city hall. And it just so happened that it had wiped out the police station and city hall. So there was actually money to build a DR plan and to solve this problem. So depending which way the river went was which one of these two places would get wiped out. So they figure, okay, if we can move all of our infrastructure, 911 infrastructure, our police infrastructure to City Hall, and we have a command post there that's temporary, we've solved the problem that police fire services will be available the next time the river runs down the mountain, which happened. So they gave us fiber. We didn't know what to do with fiber. We were a very young company, hadn't messed with fiber that much, but I knew from Wells Fargo that whenever you have fiber, you have a great capability, you have great speed, and you have great bandwidth. What we didn't know at the time was how much bandwidth we had. So we kind of, over time, started messing with that, and there wasn't anything in the market that really worked for us, so we built it. And I had a guy on my team that was an optical genius, and he goes, I know the people in Silicon Valley who can build exactly what we want, and we built a MUX that allowed us to have 30 gig of bandwidth on this dark fiber that we got. And what that allowed us to do is take their existing framework and replicate it. And we could replicate with really bad tools, with really bad large block size, and tremendous amounts of data we could move. But we moved it because we solved the problem of speed and bandwidth. So by leveraging that, we didn't change anything else in their environment. All we did is plumb some big pipes together, and we did it inexpensively. They were happy, and we had our first DR strategy. That's in late 2002, 2003. That got us thinking that, hey, this is really cool. What we really did was we stretched 2 VLANs, and we didn't know that we did it. So prior to this, in 2003, we had an architecture that was 20 miles away from one another, and we had stretched layer 2 VLANs that we could vMotion across. So they could actually vMotion from the police station to City Hall, and City Hall could vMotion whichever way it went. And everybody enjoyed that, and we thought we'd done a great thing, and we stopped. Well, we took that back to the lab, and we said, all right, we need control points on this, so we need to be able to move things at will. So we started with just a layer 2 appliance that we built out of Linux and some open source software. Wound up running for 5 years with VLAN control and the ability to move data. So we perfected that, we went to VMworld with that, and we wound up having long distance vMotion to Europe. We're the world's record holder for long distance vMotion. When Cisco and VMware went 32 miles, we went to a data center in Amsterdam from the floor of VMworld. But it happens because we cheat things, right? So buffer credits and fiber channel allow you to send things over long distance and fake time. So in our tunnel, we could turn down the volume of time and move more data, and then when we let it out of the tunnel, the natural data time was there, but everything was relative in the tunnel. So when you look at how you solve problems, you have to really solve problems at a macro level, because these are all the problems that we're going to run into when we try and do this. So putting the fiber in the ground, that was easy to do. Everybody has it. It's easy to get access to. So data center D and E are about 1.5 miles apart. So we talk about latency. Data center F is in Las Vegas. So we wanted to stay in light from a wave perspective. I didn't want it handed to me with any other medium between me and the person providing the light. I wanted to manage what I was putting in the data and how we got that. So when you look at the 10 gig wave that goes between DC-D and DC-F, that's 37 milliseconds. When you look at the 1 gig wave that goes from DCE to DCF, that's 17 milliseconds. That's about the fastest you're going to get to Las Vegas. And it takes a different route. That route goes through Salt Lake City. The other route goes through One Wilshire, which is the tie point if you're going to go from Northern California back east. Then the next thing, that once you have the fiber, you have the ability to have the bandwidth, and you can get to whatever you want to do. You can make up for any things that we didn't get right because we can put bandwidth at it. Next thing is we like to deal in waves. So whenever our WAN, we put waves in the WAN. And you can get this from any of the telco vendors that are out there. A common name for it is EPL, Ethernet Private Line. That technology allows us to have the rules of Ethernet apply. And what happens is we get it in a latency that we can deal with. The latency is usually about 1 to 3 milliseconds of latency. Once you have that latency, that's the secret, because Ethernet doesn't fall apart. Ethernet, when we put it in different protocols that are WAN protocols, they're not made for real-time communications. They're made for store and forward technologies like email, like a little bit of bursty things like the web, right? The average packet size on the internet is 212 bytes. So I don't have anything that wants 212 bytes. My ACK is probably bigger than 212 bytes when I have it coming back at me. So those are things that start to break down if we say we're going to choose the wrong medium. And we'll talk about this in more detail and how we found this. The next thing is we can create bandwidth for free virtually. So when you guys here, you're going to be in a MAN area. You're going to have access to a fiber kit. And when you come into your data center where you're working from, that's your restoration data center, you're going to be able to put passive optics, passive devices that are able to break the waves of light. So when I started out, we could only get 8 waves of light. That's in 2003. 8 10 gig waves that were cost effective. If I went outside that boundary to DWDM, I was going to pay a lot of money. So today I can get 88 waves for about $3,000. I can bookend a strand of dark fiber and put 88 waves of 10, 1, 10, 40, or 100 gig. Light, so light is our cure to the problem of bandwidth when we build these networks. And it's relatively inexpensive. So what are we putting on it, right? So we have real-time applications, video applications, store and forward type data sets, and then replication. And we pay a lot of money to get replication to work, right? I heard EMC quote a number one time that SIDF replication was $1 billion market in compression to stand between their Symmetrix line of storage replication. So if we're spending that kind of money to get things to work, if we can spend the money to solve the problem and grow the bandwidth when we build the network, we're really downrange pretty far with the solution set that we need. This slide really just talks about really what you guys are building is you're building a data center as a service, and you're building a technology stack that allows it to be, the abstraction layer is being leveraged, and you're allowing all the different agencies to come to a head end that you're getting economies of scale for, right? So virtualization gives us the economy of scale. So once we figure out how to escape the system and get more and get greater density, then we start to get a price avoidance that we're not paying for things that we don't need anymore if we were to buy 88 servers, right? We don't need 88 servers. We can get that probably in 6 servers today. So the next thing that starts to happen is server virtualization comes in and it changes the dynamic of the data center. So when I was at Wells, we had probably 3,000 servers in one room. That meant that we had to have about 6,000 ports on the floor because everything was dual homed. And then we had an out-of-band manager, so we had another 3,000 ports for out-of-band management of all of the servers. So that was a dream for the hardware vendors because we're going to sell a lot of ports. What happens when we virtualize? Those ports go away, right? So today, well, when I started virtualization, we were lucky if we got 10 servers to a host, 10 guests to a host. It's not uncommon today to get 60 on a host, okay? So we just took out 60 ports that were physical ports in the data center that now are virtual ports. But if we're not leveraging the virtual switch and we don't choose the right virtual switch, we still go up to the top of the VRF and come back down to talk to a server. We don't want that. You want to talk to the server in the silicon in the NIC card on the ESX host. So that dynamically changes bandwidth functions, it changes latency, and it changes how much we can do in a short amount of time if we don't go up the stack and come down the stack. So it's a fundamental change where we have to work with the networking team to say, hey, this number of ports has come out of your environment. If you still want to be in that world with us together, because virtualization can now replace the network, guys, because we have something called the port group. The port group is synonymous with the VLAN tag, and you can almost defeat any strategy from a virtual perspective that the hardware guys have put in place by messing with the MAC address, by messing with the mask, and by playing a man in the middle. So from a security perspective, we have new challenges that now exist in that environment. So one of the things that starts to happen is we think about it as a fabric, not a network anymore. We don't care about the traditional 3-tier model. That goes away because the 3-tier model now is a network card that can virtually switch. So I can buy a network card from a vendor that has 16 million send and receive queues that I can pair together for virtual machines to switch on the network. Switch on the network card. They never leave the ESX host. So that has a tremendous impact on what we can do, and we're cheating time. So cheating time allows us to get away with other things where we don't have a great virtualization strategy. The next thing that we have to look at is when we build our DR strategy is how do we replicate what the physical world is that we have? Oh, a question? Oh, okay. How do we replicate the physical world with virtual infrastructure? So you'll hear the term virtual network function. How many folks have heard of that? Single root I/O virtualization, heard of that? These are ways of taking a network card and physically dividing it into instances of the network card. And so today, it's very easy to take a network card and get 8 instances of the network card in an ESX host. Any Broadcom chip that ships today can be n-parted into 8 instances. If you're on Cisco Gear sells a card that goes to 64 instances of that environment. Now what that allows us to do is create a security posture with that by mapping the uplinks to their own virtual switches. So there's no shared point of the instance of the hardware at the hypervisor layer that's commingled. So by starting to build with these components in the network, we're building a stronger security posture, we're getting value, and we can virtualize it and carry it with us when we have to move the data center. So this is the holy grail of what we really want to do. We want to preserve the address space, right? Nobody wants to remap their address space. How many folks have remapped their address space in a DR program? It didn't work too well because you have hidden things that don't use DNS, don't use name services, they're hard-coded IP addresses, and when you turn it up, it doesn't work. And forever to find what that guy did 15, 20 years ago when he hard-coded that program that leverages an IP address. So we want to preserve the address space. So preserving the address space is really, when you look at the virtual service network, that's a stretch to layer 2 VLAN. Back in the day, that was as good as it got. Now, we can create layer 3 on top of that. We can do MAC isolation. We can group sets of MAC addresses together as flows and secure the environment from a flow perspective at the MAC layer, and be able to present a network that can do anything that you do in the physical world at your main network. We can do it for less and cheaper, and it's portable. So next thing that happens is the explosion of MAC addresses, because we're taking that down and we're moving it into the ESX server. So if we're using top-of-rack switches at the top of our ESX server farm, they don't work anymore because we can actually blow through the top-of-rack MAC address tables that they were built for. And we don't see that hardware changing because it's much harder to get revolutionary change at that layer because it takes a long time for that to flow through. So what we really need is this flexibility that the physical topology is independent. We have layer 2 and layer 3 services, and we don't care where it is. We can move that between data centers. So now, how many folks make mistakes in the core of the network and have brought down the network? I have. In fact, my first day at Wells, I forgot what side of a 252 mask I was on. Well, I took out about 50 ATMs that day. I thought I was being escorted out of the building, but they just wanted to get me away from the away from the router. So, and then luckily I got the mask right, and I never made that mistake again. But what has happened is when we make mistakes, the core of the network, as a virtualization team, we don't have access to the core of the network. They don't want us to have access to that because of, issue involved there. So what we need to be able to do is use the core of the network to be passive actor to us and pass it through. So a lot of folks are leveraging a protocol called ISIS. It's very similar to OSPF, except it's used as a control plane product. It allows us to concatenate switches together at the control plane, and it allows us to create a network that is multi-tenantable. So whenever I can take the control plane of a switch and subjugate that control plane and pass it to a virtualized network, I've now created a containment model that can be passed, and the networks can sit next to one another. That's the most important part, is how do we get value and economies of scale. I've been to places that have 6 sets of 9000s because they have 6 business units in the under that agency. Well, we don't need 6 sets of 9000s. We need 6 control planes. We need 6 instances of OSPF, and we need 6 sets of VLANs that we can start to tie together. So what we're missing in that network is a third layer to be able to map things together. So what we're describing here is a technology called service provider bridging. Service provider bridging, we started using this in 2003. It was a technology that was just an ITU standard, and then it started coming up the value chain. Now it's an Ethernet standard. It's built into almost all switch stacks start to leverage this. But what it gives us is it gives us a third layer of security called an ISID. An ISID allows us to have 16 million disparate groups of VLANs. And based on the ISID VLAN tag, I can map those together so that the ISID becomes a rail. And that's how we create the control plane architecture that you need from the network. Once you've done this, then you can create isolation and a security plane that is, well, you can't say it's impenetrable because there's always vulnerabilities in the network stack, but it's pretty near impenetrable because from a hypervisor perspective, you now own the ISID and not just a VLAN tag that's managed by the administrator of the port group. So then we're allowed to start tying the VRF instances, and now we create layer 3 functionality. And I told you guys I worked at the product level for designing switches for Wells. So I was in charge of, hey, get this bug fixed to corporate so that we can produce a patch overnight and send it back to the bank. Well, one of the things that we learned is when you have a stack that goes up and down, the stack that goes up and down creates semaphores in the code. When you create a semaphore in the code, it doesn't process top to bottom. It processes in all these different out-of-band loops. So to get the full stack together, we've convoluted Ethernet to build it. And I actually worked for the guys who invented Ethernet, so I was pretty fortunate to have Mike Metcalf, bestow his view around us. And basically it was as low and thin as you can keep the stack, the better the technology is going to be, the less bugs we're going to have. So SPB is built on a horizontal stack where there's one semaphore that attaches the data plane. That's a radical departure from how our world's built today. And what it gives us is it gives us a Swiss utility knife of network capability that's virtualized. So when we look at this, how many folks, when you start working with your client, your VLAN's already used? So the client comes back to you and says, well, my stuff's all on VLAN 10. You already have a VLAN 10. That presents a problem. It means usually a new stack of equipment that sits at the same layer in the network that's parallel to your core if you can't change the VLAN. So changing the VLAN tag is an important component. Migrating between L2, L3, and masking hop count. There's a lot of things that you want to just have 2 IP addresses, so you don't care what happens in the middle. Just mask it from like a 252 address in the WAN. GRTIP shortcuts allows us to do that. So what this allows us to do then is create anything that we need at the virtual layer inside the switch stack to be at the hypervisor layer. Very important construct, and at the virtual switch layer. So I'll go through this real fast because I want to spend some time on replication. So this is the next place where we make a lot of challenges, and I made a lot of mistakes here, not understanding the impact of using the right replication strategy for the right part of the stack. So worked on a project for a casino that made $2,000 a minute on slot play. If we were down for 20 minutes, we all got fired. So I was the vendor that put that deal together, and I didn't want my name in the paper. So we built a disaster recovery strategy for, I didn't tell you the worst part. The worst part was that 32 SQL servers were running all of the slot machines. And that sounds like, hey, how is this going to work? It's going to be a really bad day and we're all getting fired. But it didn't work out. It worked out really well, but there was some heartache that we learned. But what we learned was the replication point of how we capture the data is the most important part about how we do this. So 2003 timeline, fiber channel network. We put technology in that could copy on write. So I intersected myself into the fiber channel data path, and I just journalized all the data set coming out of and going to the SAN, and mapped it to virtual machines, to that file structure. And then we were able to replicate it out of band, but still hold the timing because it had a timestamp. So the thing that we walked away with, anything that's a journalized file system, timestamps are very important to us from a replication perspective, because it means we can put things together out of time. So that technology has now become a very easy technology stack to implement in VMware. So VMware has, it's called a fork driver. VMware uses the technology, and then the folks who actually invented the technology for us on that project, third-party products are out there that leverage the fork driver. So that's the best place to get the data, because we don't have to snapshot, we're getting the data in real time, and it has a timestamp on the data set at the block level. So we can put anything back together, we can roll forward, roll backwards in time. But a lot of us don't have that luxury. We're going to deal with the SAN that we have, and we're stuck with that. That's where the bandwidth comes into play, that we can make up for a lot of things that we need to do there. I wanted to open it up for questions, because I know I'm about out of time. So if there's any questions, we'd love to take those.
I just go back at the 12 so I can't ask you decent questions. Where can I find some people that can talk like you in regard to virtualization?
Chad.
Jack.
Thank you.
Because some of the things sound fantastic. I could even talk to some of the technical guys. Really, would be in depth. Very just.
Oh, thank you. Behind.
This seems like a bit of a asinine question, but is there a particular, that you're aware of, public sector rule about what can constitute VR site besides just doing the scenario analysis?
Yeah.
For instance, when I'm looking at peering locations, I think I've got a good, you share my rack, and I share
Right.
and we've got 10 gig to be clean, but we have to be in the same municipality. I'm not aware of any river or other flood, but is there, besides just doing the hard scenario analysis, any other guidelines?
So there's going to be someone at the state who does that work for you. And here's what the rule of thumb was when I was at Internet Security Systems assessing people. It was 35 miles.
The state policy doesn't provide that type of scenario or requirement. It's all risk-based.
Okay, so it's an earthquake or it's a flood or it's.
It's risk-based,
Right.
and actually, yesterday we had a GIS session where we were looking at concept pie in the sky, you know, where potentially GIS, geocode, our state data infrastructure locations, and you can have live feeds on current natural disasters, weather, traffic. Also, for planning purposes, you can take a look at it where the faults are and where the 100 and 500-year plans are. So it was a pretty good presentation yesterday on that. But right now, there's no policy that says it has to be 35 minutes. It's do your risk analysis, do your risk assessment.
One of my clients was Kleinfelter, which they do all the risk work for the state. And so where we came up with the value was where they felt comfortable putting their data. So, yeah.
Based on risk, but we also see some stuff, I mean, there's regulatory requirements that individual departments sometimes might have that have language in it, but to her point, there's not specific guidelines around distance or cohabitation or things like that. And then also there's some of the soft stuff like politics, right? Flat out, it's not always the most popular thing to move your data out of the state of California, for example, right? So you'll hear that all the time within state departments about, well, you know, I don't know how I feel about pushing that out because there's certain political ramifications of doing something like that. And that has nothing to do with hard requirements or hard rules. It's just more of perception.
Although there are criteria and policies around out of the country.
Correct.
And we used to actually have, the data center had a contract with IBM in Boulder a long time ago. So,
And obviously your email is in Chicago now. If you're on CES, your email's in Chicago and El Paso right now. So it's not actually.
Yeah. Any other questions?
Something else, it could be, you know, you could move a 35 closer to a river, so, you know, it's risk.
Yeah.
Well, thank you.
All right.
Thanks.